In this video, we're going to talk about the divergence theorem. The divergence theorem gives us an easy way to calculate the flux over a closed surface. This theorem is very similar to Green's theorem. In Green's theorem, we took a line integral over a closed curve and transformed it into a double integral over the region enclosed by that curve. In the divergence theorem, we have a surface integral over a closed surface, and we're going to transform it into a triple integral over the region enclosed by that surface. So here's the divergence theorem. Let Q be a solid in space, and let the boundary of Q be a positively oriented closed surface, meaning the unit normal vectors point outwards. Now let F be a vector field whose components have continuous first partial derivatives. Then we have that the flux of F over the boundary of Q is equal to the triple integral of the divergence of F over Q. Now we won't be proving this theorem in this video, but I'll give a rough idea of why this theorem is true. So recall that the divergence of F evaluated at the point A, B, C is measuring the net flow of fluid out of a small box around the point A, B, C. Now let's draw a quick sketch. But instead of drawing a three-dimensional picture, let's just imagine this in 2 dimensions. So here I've drawn the vector field F, and now let's draw in our solid Q. Now remember that the flux of F over the boundary of Q measures the net flow of fluid out of the boundary. So what we're going to do is divide our solid Q into small boxes. Now for each of these boxes, the net flow of fluid out of the box is approximately the divergence of F evaluated at a point inside the box. Let's call that point xi, yi, zi. Now let's look at 2 adjacent boxes. If we think about the divergence of F at x1, y1, z1, it's the net flow of fluid out of the first box, which means it's the sum of the fluid flowing across this edge, then across this edge, and across this edge, and lastly across this edge. The divergence of F at x2, y2, z2 is the net flow of fluid across the second box. So it's the flow of fluid across this edge, this edge, this edge, and this edge, all summed up together. Now if we consider the sum of the 2 divergence of F at x1, y1, z1 plus the divergence of F at x2, y2, z2, so what we'll be adding is the flow across all of the edges. Now let's look at this middle edge here. And suppose that my vector field points to the right like this. When I'm calculating the divergence of F at x1, y1, z1, then the flow across this middle edge is going to be some positive quantity because fluid is flowing out of the box on that edge. However, when I'm calculating the divergence of F at x2, y2, z2, the flow across this middle edge is going to be some negative quantity because fluid is flowing into the box. Along the middle edge, whatever flows out of the first box flows into the second box. So when we sum up the 2 divergences, the flow along that middle edge cancels out. When we add the divergence for 2 adjacent boxes, we get the net flow of fluid around the boundary of those 2 boxes. So now let's sum up the divergence of each box within the solid Q. When we do that, we get the net flow of fluid across the boundary of boxes within Q. So in our picture, it's the green boundary there. So our last step is to take the limit as the size of the boxes go to 0. As the size of the boxes get smaller and smaller, their boundary would approach the boundary of Q. So when I sum up the divergence for every point within Q, I'm going to end up with the net flow of fluid across the boundary of Q. And that's the flux of F over the boundary of Q. So that's the rough idea of why this theorem is true. Now let's look at some examples. So in this example, we have the vector field F with components x plus z, x plus y, and y plus z. And let S be the boundary of the unit cube whose vertices are listed there. We're asked to find the flux of F over the surface S. So here we have a picture of our cube. Now if we wanted to calculate the flux of F over S like we did before, this would be a lot of work. We would need to break S apart into its 6 sides, then calculate the flux over each of those sides. But with the divergence theorem, this is much easier. So first, let's find the divergence of f. We have div f equals the partial derivative of the first component with respect to x plus the partial derivative of the second component with respect to y plus the partial derivative of the third component with respect to z. So in this case, we just have 1 plus 1 plus 1, or 3. Next, we need to identify the solid Q whose boundary is S. So in general, all we have to do is take the interior of S to be our solid Q. So in this case, it's the unit cube. Now we'll find the flux of F over S using the divergence theorem. So we have the surface integral of F dot n ds is equal to the triple integral over Q of the divergence of F dv. Well, our solid Q is the unit cube, so I'm going to be integrating from 0 to 1, 0 to 1, 0 to 1 of the divergence of F, which in this case is 3, in the order dz, dy, dx. For the unit cube, it doesn't really matter which order you do the integration in. When we compute this triple integral, we just get 3. So as you can see, the divergence theorem makes it much easier to calculate the flux over a closed surface. Let's look at one more example. So here we have a vector field F with components x cubed, y cubed, and x plus y plus z. And we have a solid Q bounded by the paraboloid z equals x squared plus y squared and z equals 1. We're asked to find the flux of F over the boundary of Q. So let's start by looking at a picture. So again, if I want to calculate the flux over the boundary of Q, this might be a little bit complicated because we need to break up the boundary of Q into two pieces. The paraboloid z equals x squared plus y squared, and the plane on top z equals 1. And we would need to calculate the flux over both surfaces. So let's use the divergence theorem. First, let's calculate the divergence of F. Div F is equal to the partial derivative of the x component with respect to x, so that's going to be 3x squared, plus the partial derivative of the y component with respect to y, so that's 3y squared, plus the partial derivative of the z component with respect to z, so that's plus 1. Next, we need to describe the solid Q. Here, I think it would be best to use cylindrical coordinates. So first, let's figure out the bounds for z. Well, z is bounded below by the paraboloid x squared plus y squared, and bounded above by the plane z equals 1. Next, we need to project the solid down to the xy plane. And when we do that, we see that we have the unit circle. So, in cylindrical coordinates, my circle can be described by r between 0 and 1, and theta between 0 and 2 pi. So the flux of F over the boundary of Q is the double integral over the boundary of Q of F dot n ds. That's going to be the triple integral of the divergence of F. So that's 3x squared plus 3y squared plus 1. And then we're doing this in cylindrical coordinates. So we have r dz dr d theta, where my z's go from x squared plus y squared to 1, my r goes from 0 to 1, and my theta goes from 0 to 2 pi. So writing this in cylindrical coordinates, we have the integral from 0 to 2 pi, integral from 0 to 1, integral from r squared to 1, and then I have 3r squared plus 1 times r dz dr d theta. I won't go through the details, but when you integrate this, you get pi. So that's it for this video. In our next video, we'll look at Stokes' theorem, which relates line integrals to surface integrals.